frog jump. So the stones, the position in units in sorted ascending order, determine if the frog can cross the river by landing on the last stone. If the frog's jump was K, its next jump must be either K. Okay, 3 choose. So this is a DP problem because it tells us the selection and the state is true or false if we can walk like step on that place. And let's see. Well, for example, this one is true is because we can step to 1 step to 1, and the ones can jump 2 units to 3. 3 can jump 2 units here, and here 1 unit here. Units, 2 units, 2 units. At 8. Oh. This is 2 units. 2. Oh. This is just from 5 to 8. This can jump 3 units. So from 8 we can jump 4. From 12 jump 5. Okay. Let's see. Let's first look at matrix. 0, 1, 3, 5, 6, 8, 12, 17. And we can write down how many steps we can go here. It's just 1, 2 at the index here. 0, 1, 2, 3, 4, 5, 6, 7. Index. Oh, this is index. This is position. This is the step. So at here we just have 1. Here you have 0, 1, 2. Here at 3 we can, because the jump is 2, so we can jump. Okay, jump is 2, so we can jump 1, 2, 3. And for 5 here, because we jump 2, so same 2 and 1, 2, 3. And but for 6 here, we can jump 3 from 3, so I'll jump 1. So we have 0. Oh, 0 actually doesn't mean anything here. 3. So 3 is 4. And let's look at 8 here. It can jump 2 steps from 6 or 3 steps from 5. So can be 2, let's see, can be 2 or 3, and minus 1, and add 1, so it's 4. It's 1, 2, 3, 4. Then for 12, we jump 4, so should be 4, and then 3, and 5, and okay, then last step, we jump 5 to the 17. So this is like we just record how many steps we can, how many like units we can walk in each position. So if we can, so this is very important to know if we can step on 17 here or not. Let's see. Since we have here is 8 like you stones, so we increase 1 step, 1 unit at 1 time. So at most we can increase 1 6 times, or 7 times, 8 stones 7 times. So at most we can walk to like 8 step. At most we can walk 8 step. So the matrix should be the length of the stones and multiply the okay, so it's a square, I think. When every time I apply 1, 2, 3, 4, 5, 6, 7, 8. Okay, yep. At most is 8. So the DP dynamic programming, this matrix should be let's see, 0. The length should be this, and multiply the n, and then for this, and so this is our DP matrix, and let's fill out the matrix from top left to the bottom right, and let's first initialize the first place. Maybe we don't need 0. We can start with 1. Let's see. Yeah, we can add 0. Error is just 0. 1, 0, and 1. It's true. That's true. That's already is true or false. Here, so let's say it's false. And then the first line should be here should be 0. Let's see, here should be true. We can work 1 or not 1. We can work this 1 step, only 1 step, right? Only 1 step. Okay, and then here we can okay. 0, 1, 2, 3, 4, 5. Okay. How to fill out this? So we have dp00 should be I think we don't need 0. If we have true here, let's start with 1 to 8. So row can -1, but still need this much. So here we have true dp. So dp00 is true. Okay. And for this, we the transition function should be, let's see, dpi means the ice stone, j means the step, so dpij should equal to dpi minus 1, the previous one, and then it's a step j. If it's if it can walk to the ice, means stones and I minus 1 plus this dpi minus 1j equal to the stones I. Means here is this is 0 plus the 1. Step should be j. Step is j. J is step. Step is this. So they will be equal. Here. Yes. Then it can also come from maybe not I minus 1. Maybe some stones even before the I minus 1, I minus 2. So maybe we need to check k from 0 to I minus 1. See if stones is k plus j equal to this stones I. And then we can update. But it should be this. But if this is true, yes, if dp k j and first it should be true, then we can jump this. For example, here we have position 3 and jump from 1 because from 0 to 1. So dpk k is 1, j is 1, is true, and 1 plus 1 no, 2 plus 1. 2 plus 1 is 3. So it can be like this. Actually, since we can jump, yes, we can jump j. If dpij is true, then dpij minus 1 and dpij plus 1 is also true. If it jumps j. Let's see. How to derive this? Oh, so if this is correct, then dpij dpij minus 1 and dpij plus 1 is also true. They are all true if this is correct. So let's see. So we have dp here is 2, and the step is let's make it n, so we can have the same index here. So let's say it's the first line 0 is true. Okay, so now we have one. Now we have I from 1. No. Okay. Yes. Let's see. Let's do this. Okay. Maybe do this. J minus 1. Let I be the this and J be this. So make Q1. This is J minus 1. J is K. This is I. I is a step number. Oh, kind of confused with the index here. So let's make this is step number. This is the index of the stones. Let's make it 8 plus 8. 1 is true. Problem here. And this should be the minus 1, J minus 1, the stone, 0. If J minus 1 plus the I, no, I just did this. Here, 0 to J minus 1, J is 1. 1 minus 1, 0. Okay. This is J. Okay. K is to J minus 1, including J minus 1. So it should be 0. So K is 0. I 0. What is I here? So 0 for 0. For k is 0. We iterate all steps if it's true. Now the I is 1 is true. Stones k is 0, 0 plus 1 is stone j, so it's correct. So we will make this all true. So this is true as well. This is true, this is true. Then we do this for the 3. So for 3, we have the k from 0 to 1 because this is j is 2, 0, 1. And for the 0, we have no values can reach here. But for just 2, for the 1, for 1 we have dp 2, 1 is true, right? 2, 1, 2, 1 is true. And stones 2 plus here 2. Stones 2 is 1. 1 plus 2 is 3. 3 is stones j. So we can mark dp2 1 dp2 dp. Okay, so this is dp2 plus 1 minus 1 j is as true. dp2 1, dp3 1, and the dp1 1 as true, like here. So this should be true. So we just do this again and again until we reach the last number and see if there's number in the last number. So how do we check that? So we just iterate dp any number, any in the last line is 8 is true, then true. Okay, let's implement this algorithm. That's from I is from like I say, should be the step is 1 to the n n plus 1 maybe is better. Here is 8, so it's n plus 1. But this is just n, yes. For the j is from the 0 to the length of n, so it's just n is n plus 1. Now we need to fill out the matrix. So first, just iterate k. For k in range, it's from 0 to j. J is no. It's to it's to j. No, it's to I. So we iterate all the steps. Yeah, other steps here. So first I need to iterate to I is a step. I plus 1. So I can take I step. Should start with 1. So 0 steps is no use. So here should be for first time. Then we see if dpi dpj and dpj. Let's see. Yeah, I think here is correct. It's j from j. Yes, so if dpik plus and stones k, what is k here? K here plus the I is stones j. Okay, we can walk to the stone. Okay, j is okay 0 to j actually. Then we can walk here, so it means we can update dp I and j is true. dp I plus 1 j is true. Because of what j steps, dp I minus 1 j is also true, right? And yes, that's it. So let's print this dp out to see if it is correct or not. Okay. Here indent. Oh, yes. Right. Okay. 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 Yeah, indent is not correct. This is out of range. Let's see. We have okay, yes, I see. This is n. This should be n plus 1. Okay. And I think something wrong here because this is all false at the last one. Let's see. If we have the third line correct, like third line is 1, 2, 3, false, 2. Yes, 2, 2, 2, 2, 2, false. I think some in previous it's correct. Then it's not correct. I don't know why. Let's see. K is all the previous stones. Then we check if for this step any previous stone can step to a stone J. And this should all be calculated before because we do from left to right. I step and a J. Yeah, this is kind of weird. Let's print something. Let's print the EP, this J's line. Like this is the guess we want to do from 0. Then 0 is 0 is, let's see. Maybe make 0 or true. What will happen? If I start with 1, Let's don't print this. It's still not correct. I think something wrong with the initialization. So 1, 0 is true. Because this is already filled, so we start from 1. So 1. So here is J is just K is just 0. So maybe I should do J here. Right here. Yeah, we have a true. Okay. False. True. True, true, true. True, 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 true. 6 true. 1, 2, 3. 6, correct? Yep. Then false. True, true. True, true, true. False. True. True, 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 true. Yes, false, false. Yes, correct. Then false, false. True, false. True, true. True, false. Also correct. Then false, false, false. True, 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 true. Oh, I see, I see. I got it, I got it. I already did the correct thing, actually. So we just return any how to say n. Yeah, all false? No, I see some. I see some here, right? I see some true here. What happened for image? And I want to see the last line column. Print. Last column. Oh no. Area line. Last column. True, right? So just return any. Oh, it will. Okay, for I in return true, return false. What happened? Last, no, I column, last one, return true, false, false. Time limit error. It's weird. I think the DP shall work. I guess this is because this is huge. I think K. I don't need to go so far away. There's only 8 maximum steps here. Go. Yes, let's see. So, for example, for 8, you can only walk 5 steps. Only walk 5 steps at most. So don't need to start from 0. Let's look at how to optimize this code. For 3, let's see. Okay. Looks like okay. So this shall be very similar to this one. So we have false and false, and false one, yes, one, yes. Here, kind of different. Oh, I don't need to check so many. Oh, I should calculate the distance. And see the distance. Okay. I got it. It's doable, but it's time complexity too high. So here, let's see, we still do it from n, and this is to I. Let's see. For each, we need to go to see the distance is stones I minus stones j. Then we see if it can work this step. Yes. If distance is smaller than 0 or bigger than something, distance is bigger than n, and we return. Oh, then continue, I think. Yes, correct. Or we don't have this PP distance j. Not distance j. We just don't do it. Okay. If it does work, we can jump. Then we update dp dist and the n, because we don't need to fill out all the matrix here. So just fill out the dp dist with a j with I is true, right? Then we check if I then is dist plus 1 is smaller than or equal to n, then dp dist I is also true, or plus 1 is also true. Then the minus 1 is greater or equal to n, to 0. Okay, so, right. Okay. And we don't need to. Yes, let's see if, yeah, we just need to check if I is n minus 1, then we just return true. Otherwise, we return false. Yes. Yeah, this is close to what we already write here. But we just need to do the for loop for each stones and another inner loop for stones before. Use distance between the distance. We don't to fill out a whole matrix. Yes, this is the optimization check. Yes, cool. The time complexity should be O(n) squared, right? And dp and square to loops. Okay. And there are other solutions. Let's see. As we think of it as a like DFS or BFS, it's also very doable. Let's see. Let me see. I think that DP is best solution here. This is just we check if we can reach somewhere. We just add the step to each place. And we try to update every possible next position. Yeah, I think this is also not that complicated. Which one is the fastest here? Oh, I see. What is this? Okay, this is one is B. This was DFS, BFS, I think. Let's see what's the thinking there. So we use a set. Okay. DFS iterative. Let's see. Let's implement this. Okay. So just to copy this here. So let's see for the DFS. The DFS, we okay, we try each possible like path until we reach the end. Every time we add a position and its step. Okay, let's see. And if we reach a position with the same step, then and that's not to be not generate that position. So we start with we have stack. So we start with position 0, step is 1. While stack, pop it out. Okay, let's make it 0. Be consistent. So if for jump in current 1, if maybe you can jump to somewhere very far. How do I know which place it jumped? Yes. Is it any search to search for the place it jumped? Okay. Okay, in the set. Okay, yes, right. We need to have a set. So unit x stone set. Yes, set stones. So let's see. In the let's see, jump. -1 to current 1. That's 2. If jump, if stones print 0 plus this jump in the stone set. This means we can jump to that place. So we need to check if and this should not be there. And its position and its jump not being visited, then we can generate. Then we can stack append this. Okay. We'll take that. This one. So this is how we add this. We need to check if we reach the last stone. If the S stone's last element return true, otherwise return false. Does it work? See. Line 12 turn 0. Index. Let's see what this can be. 8, 2. Yes. If current 0 should be smaller or equal to most length of stones. And weird. It's weird. Yeah, it's really weird. How does it? No. Turn 0. It's just index. I don't need stones here. Just keep the unit. You no longer need stones. You should be correct. Yes. Okay, let's see. Submit. Yeah, passed. So this is clear. The time complexity. Because every time we have 3 possible places to go, and we have n stones, so time complexity can be n to the power of 3. N to the power of 3. Right, as DFS. Use memorization. Okay. Yes, this is Leetcode 403. Thank you.